C24, and that is about the contents, about the learn the block diagrams and signal flow graph. And for this one, the state space representation, that is for, in terms of our textbook, that is chapter 3. I decide I will skip this for a moment for the time being. This one, I think I will try to combine with chapter 11. Okay, that'll be more appropriate. So if you go to the C24, and we have done the block diagrams, and here quickly show you the content here. Okay, so this is the content we did in this week, Monday, and Monday. Okay, whatever. Okay, so let me move on. And here, that time, I don't have time to go over this page. And so for this page, basically here we have the transfer functions. And this one is related to your homework. In your homework 2, question 1. I think the 7, I forgot. So basically here is this. If we consider a simplified transfer functions and output input, and this like this is a second order. And then, for example, if you are able to find the roots of the denominator equations, then basically the roots are the poles of the system. And like the homework question 1, I ask you to calculate the poles and zeros of that question. Basically, that fitting into this format. So for the question 1 and the 0, I think for the homework 1, that is into this kind of the template. And so in this case, there's a no 0, so you simply answer your question none. And for poles, you simply solve for the roots of these. Okay, and then I ask you to plot the poles here. So this is the real space and imaginary space. So for whatever, let me make one example. So say the transfer function y over r equal to s squared plus 4s plus 8. I think that exactly is our homework question. The homework problem. I just made it. Okay. So now for this case, then the characteristic characteristic equations is s squared plus 4s plus 8 equal to 0. So s1, 2 will be equal to minus 2 plus j minus 2. So here the location of the poles is here. Here is minus 2, and here is 2j, and minus 2j. Okay, here and here. Okay. And then I ask you to plot in the time domain. Is that right? So I also ask you for the second questions in the time domain, what is the response of the y when RT is we call the unit impulse input. So basically, YT is called the unit impulse response. Okay, a response of the system to unit impulse. We call that is called the unit impulse response. So what is a unit impulse? So for the unit impulse is this. If this is a time, and then for the unit impulse I provide to you in the problem statement is delta t. And if you remember in the beginning when we introduced the Laplace transform tables, and here is a delta t, which means at a time equal to 0, initially we give an impulse signal, and then the magnitude equal to 1. This is called the impulse. Impulse, basically, if you really want to approximate, basically here is this. It has a very short period and that period basically approaching to 0, and that pretty much is like this. This is the impulse, and I cannot control my force magnitude, but this is the impulse, okay? And if we have the different, so this is the delta t. Okay, if we have delayed impulse, for example, applied at here. For example, if we applied at time, say here t, say equal to 2, okay, so if we delayed our application of the impulse at here, then this function in mathematics is denoted by t minus 2. That is the representations of mathematics for the impulse functions, okay? So we have the impulse functions, then the plus transform of the impulse will be equal to 1. If you look up the tables, that is equal to 1. Okay, so that means if you want to look for this one, so basically you calculate is this. Y of s will be equal to the transfer functions multiply with r of s. So when r is a unit impulse, then the r of s will be equal to 1. Okay, so simply you calculate is 4s plus 8. So yt, the unit impulse response of the problem will be you simply calculate the inverse of this one. Okay, and proceed, do your calculations, finding what is the contents. That should be the sinusoidal function confined in the envelope of exponential decay. That's the solution here. So basically that will be something like this. Okay? To draw it, so that is for the question 1. And now the other question is this. That is the content we want to talk about here. Okay, so here we do the formulations, and that is just like our homework here. So now we want to see is this. So right now, for this system, for this calculation, for this example, we have the transfer function like this. And then we have the pulse location. Corresponding, we have a unit impulse like this. Compared to the other example, say we have the different system. Let me make up one. S squared plus, say, let me say 10s plus 25, 50. Okay? And I can tell you the pulse for this one is minus 5 plus 5j. Okay, so in this way, let me overlap the poles here. So using the, let me make another one. 10, 5, 5, minus 5, 2j, 29. Let me make up this. Okay, so basically this will be 2j here. Okay, so for this case, let me using the colors. So poles are the, how to calculate this one. Basically, you simply put the s squared plus 10s plus 29 equal to 0. Then you'll get the roots. S1, 2 will be equal to this one here. Okay. So let me label the location of this pole, and that will be corresponding will be here and here. And that locations will be, this is minus 5. Okay. So you can see, compared to the two systems, for the two in their poles, basically for my design here, they have the same number, the magnitude of the imaginary part, but only matters is the real part here. And for this system, if you can overlap, you can repeat the calculation to calculate the unit impulse response of this system. Then you can calculate and to draw this response here, then response will be similar, will be pretty much like this. For this kind of system, it will oscillate quicker. and it might delay quicker. Okay. And if we change the numbers, then everything will be changed. So in this way, the MATLAB, if you can able to write up the MATLAB program and do the parametric study, you can see, you can learn the curve, the response of the curve. And so that is the context here, how the locations of the poles will relate to the system response. This is one quick example. If the location of the poles is farther away from the origin, it would oscillate quicker. It will delay quicker. Okay, and here it's going to give you a systematic justification. So if we only have one real root, and the response will be like this. Why? And so again, for this system, let me do this calculation here carefully for you. So here, if our transfer functions is this, let me make up one. In terms of my noting here, this is the output xs. And this is our system. And this is our input. Okay, transfer function, and then input and output. Okay, so transfer function here. So here for our input, for example, rs equal to 1. So which means this one input is rt. Okay, so here we talk about is the unit impulse signal. So here, accordingly, here we talk about is the unit impulse response. Okay. So here we have those kind of get ready for calculations. For example, when GS equal to, using this example, is A, say S minus S plus A. So therefore, X over S will be equal to GS times RS. Okay. Again, the X equal to G times R, and right now our R equal to 1. So basically, is a GS. And this one will be equal to A S plus A. So therefore, xt will be inverse of the x of S, and then that will be inverse of A S plus A. Then here that will be equal to A times E minus AT. Okay, so that's the calculations. So once you have this one, you simply use the MATLAB to draw it, and that is a curve like this. And if you play the numbers, if you say, let me get this slide. So say if you play certain numbers, and here, for example, say for A equal to 1, okay, and then say when A equal to 1, then initially the molecule was starting from 1, okay. And say if A equal to 1 here, then corresponding is this curve. Then let me make another example here. So if you try another parametric study, say A equal to 5, then that will corresponding is this one here. So this corresponding is A equal to minus 5. And last time I told you how to overlap two curves on a single drawing. So in this way you can play around, and from here you can see and the impact of those numbers here. Okay? So we can go to the next example here. So The next one is this one. So here, let me make one example here. So say GS will be equal to AS plus B. My goodness. You know how to do it. So let me pick one example. Let me pick one example here. Okay. So here, the same thing here. So that will be equal to GS. And this one will be S squared plus 4S plus 8. And this one, if you do the Laplace transform, and then xt will be inverse of this one here, S squared plus 4S plus 8. If you do this carefully, and again, that is our contents of homework 1, right? If you do this carefully, e minus 2t, 1/2 sine 2t. I provide you the answer here. Okay, so in this way, are you able to draw the MATLAB curve? Yes, you should, because last time I gave you the MATLAB commands for this one. So you draw it, and then you have certain oscillation curve, but basically this one is confined with certain profile. Okay, the profile is the, for example, exponential in decay, say minus 80, something like this. Okay, so in particular for this example, you can draw it. Now, once you have finished the whole line, then you can change the numbers. For example, the second example you can try is this. GS is equal to 1s squared plus 10s plus 29, just like the example over there. So you repeat the calculations. Okay, so here you can do these things. X over s equal to certain something, and here is GS. And basically s squared plus 10s plus 29. And again, you take the inverse Laplace transform. Okay, inverse Laplace transform. Let me do the calculation here. S plus 5 squared plus 2 squared. So this one will be equal to e minus 5t times sine 2t 1/2. Okay, so here is 1/2 e minus 5t sine 2t. Okay. So from here you can play and overlap the two curves, and let me draw this one here quickly. So for example, if this is time and this is our response, for the first one, 1/2, this is let me define the profile of the decaying first, and sine 2t, that will be something like this. Okay, and from peak to peak, and here is our period, will be equal to 2 pi divided by the frequency 2. Okay, and now for this one, we can draw again the profile will be something like this. Then oscillation will be okay, because the two curves are oscillating at the same frequencies, so their peak must be ended up the same. And for the blue one, if you can really draw a pretty curve in MATLAB, then you can see the blue one will decay faster than the previous one. If we would change the numbers here, say, let me make another one. So say if this one rather is 29, say 34. If that number is 34, then this will be 3 squared. And then under that situation, this will be 3t. Okay? So for that case, this 3t, then for this curve, it will be oscillating quicker. Okay? So those kind of things providing for you. So corresponding to here, here for this example here, let me draw the curve here. So the location of the poles. So here is 2 minus 2 plus 2j. That corresponding to this system. This system has the pose locations. For the blue one, that pose is here, and minus 5 plus 2j complex conjugate. Okay. For the red one, that has the location here, and minus 5 plus 3j. So hopefully by using your observation and deduction, hopefully you can summarize using your own words about the effects of the location of the poles on the dynamics of the system. From here you can say, if I would do this one for you, you can see the farther away the location of the poles from the origin, the quicker it decays. The larger the oscillations, which means the quicker oscillation, that meaning it has the larger magnitude of the imaginary part, etc., etc. The most challenging part in burning control or vibrations is connections between the information in the frequency domain to the time domain. Those information are in the frequency domain, in the complex domain. Those are in the time domain. So right now, for these contents here, I'm trying is actually to help you to bridge the connections between the pieces. There's no unique way. The only best, I would recommend the best way is you just do a few examples, your own exercise. From there, you should quickly have certain intuition will be built up. Okay? So that is this one.